An approximation algorithm. In this section, we sketch one instantiation of the missing details of algorithm tree-Nash that yields a polynomial time algorithm for computing approximate NE for the tree game GM. The approximation can be made arbitrarily precise with a greater computational effort. Rather than playing an arbitrary mixed strategy in the closed interval between 0 and 1, each player will be constrained to play a discretized mixed strategy that is a multiple of tau, first time tau to be determined by the analysis. Thus, player I plays Qi, which is chosen between among the set 0 tau, 2 tau until 1, and the joint strategy Q arrow falls on the discretized tau grid, which is is chosen among the 0 tau, 2 tau until 1 to the n. In algorithm tree-Nash, this will allow each table T of VU passed from vertex U to child V to be represented in a discretized form as well. Only the 1 over tau square entries corresponding to the possible tau grid choices from U to and V are stored, and all computations of best responses in the algorithm are modified to be approximate best responses. To quantify how the choices of tau will influence the quality of the approximate equilibrium found, which in turn will determine the computational efficiency of the approximation algorithm. We appeal to the following lemma. We note that this result holds for arbitrary graphical games, not only trees. Lemma 7.4, let G be a graph of maxima degree D and let Gm be a graphical game. Let P arrow be a Nash equilibrium for Gm and let Q arrow be the nearest in L1 matrix mixed strategy on the tau grid. Then Q arrow is a D tau NE for Gm. A proof of lemma 7.4, which we omit, follows from about on the L1 distance for product distributions along with an argument that the strategic properties of the ME are preserved by the approximation. We note that the original paper, Kearns et al. 2001, used a considerably worse L1 bound that was exponential in D. However, the algorithm remains exponential in D simply due to the representational complexity of the local product distributions. The important point is that tau needs to depend only on the local neighborhood size D, not the total number of players N. It is now straightforward to describe the approximate tree-Nash. The algorithm is identical to algorithm tree-Nash, with the following exceptions. The algorithm now takes an additional input epsilon, and for any vertex U with a child V, the table T of VU will contain only entries for U and V multiples of tau. All computations of best responses in algorithm tree-Nash become computations of epsilon best responses in algorithm approximate tree-Nash. For the running time analysis, we simply note that each table has 1 over tau, square of 1 over tau entries, and that the computation is dominated by the downstream calculation of the tables, step 2D of algorithm tree-Nash. This requires ranging over all table entries for all k parents, the computation of order 1 over tau, square of 1 over tau to the k. By appropriately choosing the value of tau, in order to obtain the required epsilon approximations, we obtain the following theorem. Theorem 7.5, let Gm be a graphical game in which G is a tree with n vertices and in which every vertex has at most d parents. For any epsilon greater than 0, let tau be big O of epsilon over D. Then approximate tree-Nash computes an epsilon Nash equilibrium for Gm. Furthermore, for every exact Nash equilibrium, the tables and the witness lists computed by the algorithm contain an epsilon Nash equilibrium that is within tau of this exact equilibrium in L1 norm, the running time of the algorithm is polynomial in 1 over epsilon n and 2 to the d, which is polynomial in the size of the representation Gm.